All right, today we are going to be talking about the force of gravity. And my favorite thing about the force of gravity is it sets up a lot of really great nerdy Yo Mama jokes. Before we get to the Yo Mama jokes, let's talk about the force of gravity, or let's talk about the mystery of gravity itself. Gravity is the attraction between objects that are made out of stuff, made out of mass. If you have mass, then you're automatically exerting a gravitational attraction to everything else around you. But it's a very weak force. So we tend not to feel a gravitational attraction towards people unless we happen to be Yo Mama. That was my first one. Setting this up, if we have two objects, whatever their masses are, m1 and m2, there's going to be an attraction there, but it gets weaker the further apart they are. So you guys may notice that even though the sun is much, much, much larger than the Earth, it has way more mass, it's so far away from us that we feel very, very little attraction towards the sun, whereas the Earth, which is very close to us, gives us a much larger force of attraction. I watched somebody do the calculations at one point. It turns out that while the sun is very, very massive, spiders on Earth tend to be very close, and there's a pretty close to the same attraction between you and all of the spiders on the Earth and you and the sun. Like they're pretty close to each other. So that's a fun calculation. So going through here, though, this is the formula for the force of gravity. This is called Newton's law of universal gravitation. And this is the right one to use if we're dealing with a problem that involves other planets or being far away from the Earth and things like that. I'll talk about in just a minute what we use if we are near Earth and why it's an okay simplification. But let's go through what these different variables mean. This is the big one that probably doesn't already make sense to you guys. And this is called the universal gravitational constant. It's a number that, as far as we can tell, is the same everywhere in the universe. The number for it is about 6.67 times 10 to the negative 11th. Sadly, we can't just simplify that, round it up to 10 or something. That's a little bit too much for me. And then the units of it are newtons meters squared over kilogram squared. All those units are for is so that when you have g and you divide it by r squared, you'll cancel the meters. And when you multiply it by the mass and the mass, you'll cancel the kilograms. So really the only thing that the units do there is to get it into newtons. So you can kind of just ignore the units. It's the number that's going to matter for us, unless we use the units just for the purpose of double checking your problem and making sure that you're going to get it right. So there's the force of gravity. This is each mass. And what's interesting, so this is called, mass one, mass two. It doesn't matter which one's which. I said mass one was on the left, mass two was on the right, but you guys know how math works. If I multiply 2 times 1 or 1 times 2, I still get the same result. It doesn't matter which one of these comes first, which one's M1 and which one's M2. It just matters that they're both in the equation. And that's because this is Newton's third law. If the force of Earth is pulling me down with I don't know, I think it's roughly 650 newtons, then I am pulling back up at the Earth with 650 newtons. All masses attract all other masses, and they always do it in an equal and opposite direction. So I guess what this means is Yo Mama is attracted to everyone because she's so massive. Zing, gotcha again. Okay, so got through all that. Great. This is all over r squared, which is, we need to be careful. This needs to be from center to center. You want to be really careful that you don't accidentally do it from the surface of the two objects. For example, when we're sitting here on Earth, you don't want to do the distance between you and the surface of the Earth. That's basically 0 if you're touching it, which would then mean that we'd end up having infinite gravity. The distance we want is from us to the center of the Earth, which is the radius. But please be careful. That r does not represent radius. It represents the center, the distance between the two centers of masses, which may be the radius if you're on Earth. But if we're talking about like the Earth and, I don't know, the moon, it's not appropriate to use the radius of either of those objects. We need to use the distance from the two centers. Often they'll give you the radius of the Earth or something like that in there as a red herring to see if you understand this part of the formula. So just be very careful, always center of mass to center of mass. So on Earth, though, we always know what M1 is. If we always use the mass of the Earth, then this would be a constant value. We always know that as long as you're pretty close to the Earth, the radius of the Earth could be used for R. And even if you're like at the top of the tallest mountain, Mount no, that's not right. Mount Everest, there it is. Even if you're at the top of Mount Everest, that's such a small difference relative to the actual radius of the Earth that it doesn't really make sense to even use different values. It's so close. So since the mass of the Earth is constant and the radius of the Earth is constant, then if we're using this formula, Fg equals gm1 m2 over r squared, if these are all the same value, then we could just simplify them down into a single constant, g, that would work anywhere on Earth or anywhere reasonably close to the Earth's influence. So when we use 10 meters per second, we're really using these variables together, but we're just simplifying it so we don't have to plug the same variables into the same calculation over and over again. And that's why we can get away with saying the force of gravity near Earth, but only near Earth, is mg, where this m represents the object's mass and this g represents the universal gravitational constant, the Earth's mass, and the radius. So I guess what I want to say is Yo Mama is definitely a 10 because she shares certain commonalities with the size and mass of the Earth. Zing, gotcha again. Okay, so we got all those pieces. The last thing that I want to say then is that we can also say that G must be equal to that stuff. So if we're trying to find the strength of a gravitational field or the acceleration due to gravity on a planet, that's the same thing. That's what this little g is. And those can be compiled into a single variable, gm over r. And those all together can always be used to figure out the r squared. I should square that in both mistake. So if you're trying to find it, there's the equation for it. Um, there you go. That's everything that I need to say. And please don't tell your mothers about what I said. It was a joke.